So number 3 here, we've got a contour plot given for some multivariable function. And so this is what we get when we plot the level curves and project them down into the xy plane. And so the first part of this says it asks us to calculate or estimate f of 1, 3. So 1, 3 would put me about here. And so you can see, you can make an estimate. I would say that f of 1, 3, yeah, if I'm just guessing, looks like it's kind of right in the middle. So who knows how this has changed from here to here, right? This is rising from 14 to 15, but I could say it's about 14 and a half. That's a good estimate. But then it wants us to provide an interval. What are the possible values? Well, we know it can't be above 15 because it would have to come back down to 14 to be that. It can't be below 14. So it's got to be somewhere between. So the estimate is it can't be 15 or 14, or there'd be a contour line there. So it's somewhere between 14 and 15. That's the best we can say. Just eyeballing it, we don't know how it's changing. It may not be changing nicely, linearly from one to the next, but that would be about the best you could do. And then it asks, is the graph steeper at 4.1 or 4.2? 4.1 is about right there. Maybe that's a little high, but and then 4.2 would be about right in this area here. So based on this, you can see it's level 20 and back at level 20 on both sides of this one, which says maybe it went up a little or maybe it went down a little, but it's not changing a lot, because we would have hit 19 if it were changing, or we'd hit 21 if it had gone up quickly. And so we can see it's changing more quickly here. You're hitting these lines. These lines are closer together, and so it's got to be steeper at the second point there, the 4.2. So the explanation was because of how close these lines are together and the fact that this is sitting between two 20s. All right, so the next problem. We've got this multivariable function. We just want the partial derivative at 2.1. So the partial derivative at 2.1 is going to be the derivative of x squared, which is 2x, and then derivative of xy squared is just going to be y squared, because the derivative of x squared is 1. And the derivative of all this stuff is 0. And I'm going to evaluate that at 2.1. And so when I plug in a 2 for x, I get 4, and a 1 for y, I get plus 1. So this has a derivative of 5. And remember, what that represents is the slope. If I go in the x direction from this point 2.1, that would be the slope in that x direction. And so that's kind of what we're going to use here. Is let's find the equation of the line tangent to the curve of intersection of f with the plane y equal 1 when x equal 2. In other words, find the equation of the line parallel to the x-axis when x is 2 and y is 1. So now I'm going in the x direction. And so I need, for the equation of the line, I need a point. Well, since my x coordinate's 2 and I'm in the plane y equal 1, there's the x and the y. And the z coordinates, what I get when I plug those in. And I didn't do a great job there. I should have put a y minus 1 in there, so I think I will, because I want this one to disappear. So let's pretend this is square root of y minus 1. So I get, plugging in the 2, I get 4, and then plus 1, 2 times 1 is plus 2, and then this is going to give me 0, square root of 0 is 0, sine of 0 is 0, so that's all going to go away. So I'll get a 6 for my z coordinate in that direction. So when I find the equation of and I also need a direction vector. So there's my point. Here's my direction vector. Since I'm going in the x direction, it's one step in the x direction. I don't go anywhere in the y direction. And then that slope in that x direction is 5. That's what we calculated above. And so the equation of that tangent line is, remember, you put, it's a vector. We write in vector form. It's the x coordinate plus the x component times t, the y coordinate plus the y component times t, and then the z coordinate plus the z component times t. And so there's your equation of the tangent line.